Hello again. Here is an example that deals with a confidence interval for a population proportion. And actually, we're going to look at this from real data. I've got a survey from the Rasmussen Reports .com. They do surveys, a lot of surveys and data collection on political polls and this sort of thing. But this is an older election, 2006, the California governor race. Now, this is a poll, this is before the actual election, but 500 likely voters were polled, and 225 out of the 500, or 45%, would say they'd vote for the Democrat Phil Angelides, while 220 out of the 500, or 44%, said they would vote for Arnold Schwarzenegger. Okay, by the way, here's a website if you want to check out some more of this polling information. But some questions that I have here, or that we have here, are what do the above percentages mean? What can we do with them? Is there any error associated with these percentages, and so forth? And I think if we go through and do a computation for a confidence interval on the proportion of all voters that will vote for Schwarzenegger, we can answer some of these questions. So if they just used this information to make a decision about the governor at that point, then Angelides would take governor. Well, this is not the entire voting population of California at that time, or those that will vote. This is just a likely subset of that group, and based on that, this information from that subset, can we say something about the proportion of voters that would vote for Angelides? Or we can get at that question as well just by looking at the proportion of voters that would vote for Schwarzenegger. Okay, so what I want to do here is I'm first going to identify my parameter of interest. And it is a proportion, a population proportion P, and it is the proportion of all voters who will vote for, I gotta write out Schwarzenegger. I think I spelled that right, even though it's in front of me. So we want to say something about this proportion. This will never be realized until the day or the days after the election. So we do treat it as unknown. And this is our sample information from here. We want to use this sample information to say something about this proportion, this population proportion here. And we got to decide what interval formula do we want to use. Well, there's really only one interval formula. We will use this formula, p hat plus or minus z times alpha over z sub alpha over 2 times the square root p hat times 1 minus p hat over n. Okay, we're going to use that formula in this context. And if you recall, the rule of thumb to use this formula is that we require, so let me write this out here. So to use the above, we require n times p hat to be greater than 5, or actually n times p hat greater than or equal to 5, then n times 1 minus p hat to be greater than or equal to 5 as well. Well, is that the case? Let's see here. So n times p hat. Well, what is p hat? P hat is the sample proportion of voters that vote for Schwarzenegger. Okay? That was actually already computed for us. You would take 220 and divide it by 500 to get 44%, or in this case, 0.44. N is 500. I've got 500 voters. .44 is the proportion or the sample proportion of voters who vote for Schwarzenegger out of that 500. And what is 500 times 0.44? 220. And what about n times 1 minus p hat? That is 500 times 1 minus 0.44. So we got 500 times 0.56, and that turns out to be 280. Of course, both of these are greater than 5. So we have a sufficiently large sample size to use this formula. Okay, so in order to use this formula, we need p hat. Well, we already got it. We need the z percentile and n, and those things we really already have. So as we move forward here with our confidence interval, p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. Okay, again, p hat is 0.44 plus or minus z sub alpha over 2. Now, on the side here, I'm going to compute z sub alpha over 2. So here, you got z sub alpha over 2 is z sub, again, this is 0.05, 95% confidence interval, alpha is 0.05. So we got z sub 0.05 over 2. That's z sub 0.025, and we've done this before, and hopefully you've seen this enough to know that that z percentile is 1.96. So, plugging in, we got 1.96 here times the square root of 0.44 times 1 minus 0.44 over 500. So simplifying, we've got 0.44 plus or minus 1.96. I'm going to multiply this, or I want to simplify this term. So I got 0.44 times 0.56 divided by 500. I'm doing this on the side, then I'm going to take the square root of that. This quantity, the square root term, is 0.0222. Okay, this is the standard error of p hat, right? It's an estimate of the standard error of p hat. If I take this and multiply it times 1.96, I get 0.0435. This right here number is called the margin of error. Okay, we'll come back to that in a little bit, but further simplifying, my lower bound would be 0.44 minus 0.0435, which is 3965, and the upper bound would be 0.44 plus 0.0435, which would be 0.4835. Okay, so what we have here is we're saying we would ultimately come to this problem and say we are 95% confident that the proportion of all voters who will vote for Schwarzenegger is between 39.7% and 48.4%. If you notice, it doesn't quite reach 50%, which is actually not a big deal. You don't need 50% of the votes to win. You just need the majority. But one thing I do want to say about this is here we have a margin of error of 0.0435. In other words, you can think of this as a margin of error of a little more than 4 percentage points. And often this sort of thing is presented in polls that you might see on TV or online or in the newspaper. Sometimes they call this the error points, the margin of error, associated with the percentage that they give you. And so if we interpret this, the way we interpret this is assuming that our confidence interval capture the proportion, then the 0.44, our point estimate, is at most 4.0435 units away from the actual proportion of voters that vote for Schwarzenegger. So because this thing is so wide right here, and the difference between the sample data is just 1%, but our margin of error is over 1%, it's 4%, because there's such a high margin of error relative to the difference between the two voters. An appropriate way to interpret this poll is not to say that Angelenos is going to win this thing or is really winning, but you would say that that they're neck and neck. And on TV, they use the term, this is a statistical dead heat, or they're statistically neck and neck in the race. Yeah, for this sample, there's some differences, but as we infer to the population, which is what this is doing here and here, as we infer to the population, we don't have enough evidence to say that Angelenos is beating Schwarzenegger, or is going to beat Schwarzenegger. So I think this is a neat example. Pollsters, political pollsters, are constantly using this sort of thing to try to understand how people feel about a particular population attribute, as your book says. Do people favor this candidate over another candidate? Do they favor this proposition over another proposition? And this poll data, in conjunction with this statistical method, helps them answer those kinds of questions.